Hello. Well, it's good to be back here with you again, at least, I guess, in spirit or virtually. So, yesterday we were all about Chapter 10 and memory formation. And today we're doing memory consolidation in Chapter 11, at least the first half of it. And I guess tomorrow we'll be doing the second half of Chapter 11 on memory consolidation. And then after that, we'll move on to Chapter 12 and do memory maintenance and forgetting. And so my plan was to get through Chapter 12 by the time we got to test number 2, and I adjusted the syllabus to show that very nicely. And as I was prepping Chapter 11, I found that it was a very, very long chapter. I have a lot of information to tell you about here. So I'm going to make an executive decision right now. And I'm going to modify the syllabus one more time. Test number 2 will cover chapters 5 through 11, not 5 through 12 as the syllabus indicates right now, and certainly not chapters 5 through 14 the way it originally did. So I'm backing off a bit on this. So hopefully that kind of feels like good news to everybody who's prepping for test number 2. We'll do chapter 11a today. We'll do chapter 11b tomorrow, and then we'll move chapter 12 into the next section of the course. And I think that's going to work out just fine anyway. So anyway, chapter 5 through 11 for test number 2. And that's what we're going to do, and we'll get on to the rest of it next week. Okay, so in this lecture, I'm going to focus on the role of CREB, or cyclic AMP response element binding protein, which I introduced back in chapter 5. We're going to see how it plays an essential role and even a limiting role in consolidation of memory. In fact, at the risk of giving away the punchline too early again, I'm going to tell you that one of the more fun things about today's lecture is that I'm going to convince you to change your study habits. Well, okay, I know everybody in this class has great study habits. So maybe I should say that if you are ever tempted to engage in poor study habits, I'm going to convince you to avoid those strategies, as they are truly not compatible with memory consolidation and academic success. Let's start by talking about what consolidation of memory actually is. I'm going to base my description on the Atkinson and Shiffrin model, which is also known as the multi-store model or modal model from way back in 1968. As I briefly describe this model, you may well be thinking, of course, we already know this is how memory works, and indeed, this model forms the basis of how everyone who has ever read an issue of Psychology Today or watched an episode of Dr. Phil understands cognitive psychology. But I want you to consider that prior to Atkinson and Shiffrin's work, this analysis of memory function just didn't exist. So people were not aware of these stages that we now consider to be important components of memory encoding. So here goes. We commonly acknowledge that everything you know in memory derives from environmental experiences, from sensory experience of the environmental stimuli that you encounter. This experience persists in sensory processing briefly, on the order of a fraction of a second to maybe a second or two, and this sensory memory can be readily forgotten. Certainly details are quickly degraded. But if this sensory experience has important features calling up your attention, then it can be encoded into short-term memory. This is a form of memory according to the Atkinson and Shiffrin model that typically lasts for up to about a half a minute and has very limited capacity. Actually, Hermann Ebbinghaus found that it was only about 7 bits of information. And I think I said this before. His discovery that you could hold about 7 bits of information in your short-term memory is actually the reason why phone numbers are 7 digits long to this day. Okay, from the short-term encoding, the memory can actually be used or it can be forgotten. Then, according to this model, rehearsal or repetition of items in short-term memory results in transfer of the information to long-term memory. And this transfer to long-term memory is what we now call consolidation. So I'm going to comment that this model, although very useful and a huge advance in our understanding of cognitive processes, is overly simple. If you take a cognitive psychology course, you'll learn that both short-term memory and long-term memory are much more complex than this model suggests. For example, short-term memory, an almost defunct term actually, is composed of multiple interacting components, like the central executive and the visuospatial sketchpad and the phonological loop. But I'm going to leave those for you to take a cognitive psychology course and get into those in more detail. And we've already seen the multiple different types of long-term memory, including all the different classes of declarative and procedural, or explicit and implicit memory. In addition, the model simply focuses on rehearsal and doesn't account for many other factors that can impact consolidation of memory, including emotional salience of the event, motivation to explore or retain a memory, and strategies people use to assist consolidation like mnemonic devices. Moreover, rehearsal is attributed too large a role in memory consolidation in this model. And in many forms of learning, we now know that rehearsal may not be an important factor at all. Nevertheless, this early cognitive model, which still dominates our perception of memory function, does fit with many observations in our neurobiological studies, which you should be able to appreciate from the material we've covered thus far. And although it is an important mission of neuroscience to further characterize the neuroanatomical and neurophysiological basis of concepts like the central executive, we'll see today that the basic and simple concept of consolidation also fits with our understanding of basic biological mechanisms, like Krebs, that bring about enduring changes in cell structure and function. So let's define consolidation. For our purposes, memory consolidation is a time-dependent process that transforms very labile short-term memory events into more stable long-term storage. In fact, we've already seen how this is a time-dependent process, as it takes many hours for conversion from protein synthesis independent through protein synthesis dependent mechanisms to create stable and perhaps novel spine structures that strengthen connections between neurons. And we've seen how the memory converts from a labile short-term form, where an opposing stimulation or a drug treatment can disrupt the storage and eventual incorporation of the memory, to a stable internal representation that's actually highly resistant to alteration and may endure for a lifetime, well, gradual degradation notwithstanding. In fact, a core feature of consolidation is the transfer of memory from the labile form to a stable form. The chart on the upper right depicts that as the uninterrupted consolidation period progresses, the stability of the memory, or its resistance to disruption, increases. The chart on the upper left illustrates that if a traumatic event occurs during the consolidation period, then the transfer of the early labile form to the enduring stable form is disrupted. Now, scientific awareness of this impact of trauma on memory consolidation, that is, awareness of the lability of memory in the early short-term stage, originates in early studies of patients who suffered traumatic brain injury. It was observed very often by medical practitioners that trauma disrupted recent memories, but typically spared more distant memories. And this observation was actually then made much more scientifically testable with the advent of electroconvulsive therapy for a variety of psychiatric disorders. As patients were treated with this extreme form of stimulation, it was commonly observed that recent events were zapped into oblivion. The patient would not remember any events from the hours preceding the treatment, but earlier memories would be unaffected. Of course, the attendants in this scene, along with the patient, would have no idea what the mechanisms were behind those effects. But I have a strong suspicion you can guess at some of them based upon the things that we've been talking about. Anyway, this kind of disruption, this kind of impact of electroconvulsive therapy constitutes a storage failure. The encoding of the memory was never consolidated, and the loss is permanent. It appears there's no memory trace that could ever be retrieved. And of course, this makes sense. If you disrupt the mechanisms that can contribute to LTP, like protein synthesis, the synapses don't perforate, the spines don't undergo the morphological changes we would ordinarily expect, and so the encoding of the memory really just doesn't exist. But I want to also contrast storage failure with retrieval failure. In this case, the consolidated memory exists, but we have a failure to gain access to it. This is a common experience in everyday life, and the temporary failure may be overcome later. Everyone has had this kind of experience. Like if you see someone you know, perhaps only casually, and you can't recall the person's name, or perhaps you can't even recall where or when you met that person. But later, the recollection comes flooding back. This, of course, can be an embarrassing experience, but it's a normal temporary failure that everyone experiences at some point. Perhaps you originally met that person, let's say, in an undergraduate organization to which you both belong. And then if you met that person again in the setting of the club, the organization that you both belong to, you'd likely remember the person's name and the events of your first meeting. However, if you met that person at Publix, you might fail to retrieve the memory because the retrieval cues are missing. This tells us something about the way memories are consolidated into long-term storage. It seems that memories, like the name of the person you met, are not encoded as individual unrelated bits of sensory information, but rather are encoded as a larger network of stimulus representations. Consolidation must consist of encoding of all these related stimuli in vast distributed networks of synaptic connections. Okay, let's move on to think about some experimental design considerations in the next few slides before I start to talk about Krebs and memory consolidation. We've already seen that inhibition of protein synthesis by antibiotics interferes with consolidation of the stimuli into long-term storage. Now, in fact, we need to shut down most synthesis in order for disruption of memory consolidation to occur. So if the doctor prescribes a little tetracycline or amoxicillin, I guess, it won't actually cause you to have any kind of cognitive impairment. But I also want to point out some considerations in the experimental design if we want to examine the impact of treatments like antibiotics on the consolidation of a memory. It's extremely important, if you want to measure the impact of your manipulation on memory consolidation, that you administer the treatment at the time of the consolidation period. If you administer that protein synthesis inhibitor, or pharmacological agent, or electrical stimulation, or traumatic event at time 1 on the chart at the bottom of this slide, then you can be reasonably certain that the impact, if any, would be a disruption of the consolidation process. If you administer the treatment a little later, at time 2, you may miss the consolidation period, and the memory has already transferred into long-term storage. Now, this could be a valid control procedure, but if you were looking for an effect on consolidation, an experimental manipulation at this time point would be inappropriate. And if you administer a challenge at either time 3 or time 4, you could be inadvertently impacting the experience of the training or the performance of the learned skill or retrieval of the memory. So conclusions about the memory consolidation process would again be inappropriate. Okay, so a few more methodological considerations. First of all, it's very well established that administration of substances with stimulant actions, like cocaine, caffeine, amphetamine, during consolidation, can enhance cognitive performance and memory retention on a variety of tasks. But this is only true when extremely low doses are administered. Conversely, when higher doses are administered, it's very well established that they actually have cognitively impairing actions. So in fact, we know that the common practice of staying up late to cram for, let's say, your organic chemistry exam is counterproductive. And it's made worse when students consume mass quantities of coffee or, I don't know, Jolt Cola or energy drinks, and especially when they take their friends' Adderall or other stimulant drugs to try to give themselves a cognitive boost. The amount of stimulant that will produce a very, very small boost in cognitive function is so small. It's most definitely not the dose that students opt for when they choose to engage in these study strategies. We should maybe be measuring tablespoons of coffee, not multiple cups. And furthermore, the main impact of stimulants on cognitive function may not even be some direct enhancement of the learning apparatus. Rather, it may simply be a consequence of increased arousal. I've drawn up an interpretation of the results of an experiment from back in the 1970s because the original data were reported in a series of tables, so not very amenable to presenting them here. So my graph depicts the approximate outcome of a cued fear conditioning experiment. Now, note that the timeline of the experiment is shown at the bottom of the slide, showing that the animals were trained in the cued fear conditioning, and then at the start of the consolidation period, they were injected with amphetamine or saline, or actually some of the animals were given no treatment. And then an additional group of animals was injected with amphetamine after the consolidation period, a couple of hours later. Now, this nicely matches up with the ideal experimental design I described on the previous slide, with injections at time points 1 and 2. So I guess we're all good with the design. Now, what Lyon and Randrup found, excuse me, is that rats given no treatment in the cued fear conditioning experiment, of course, exhibited some freezing when tested with the cue that had been associated with foot shock. And rats that were injected with a very low dose of amphetamine at the beginning of the consolidation period showed significantly more freezing. And if they were injected after consolidation, it had no effect. All of that fits with the story I've been building. However, the surprising outcome was that the rats injected with saline at the beginning of the consolidation period also showed enhanced freezing. And maybe not quite as much as the amphetamine-injected rats, but certainly more than the controls that were subjected to the cued fear conditioning but had no other treatment. So, was this saline effect a placebo effect? Well, I'm going to say no, because in order to obtain a placebo effect, the animal would actually have to have an expectancy about what the drug would do to it. And I seriously doubt that a rat was sitting in the test arena thinking, I just got a shot. Maybe I should expect to be a little smarter. So I'm going to rule out the placebo effect here. The reason for the effect of the saline injection appears to be the fact that the animal was aroused by the stress of the injection. And it's now actually very well established that mild stress and the ensuing arousal enhances cognitive performance slightly. But I don't think that would be a popular recommendation, Hey, students, expose yourself to a little stress so you can do better on your test. I don't think people would like that idea, but it's certainly something that we need to consider in the design and implementation of our experiments on the neurobiology of learning and memory. Another approach to understanding memory consolidation is to administer a drug or other treatment, perhaps even an inducible genetic manipulation, just after the training, at the beginning of the consolidation period, following the procedures that I've just outlined. But then test the animal twice. Once shortly after the training and treatment intervention, like maybe 1 hour later, and once perhaps about 24 hours after the training and treatment. To illustrate this, I ripped off the graphs from your textbook because these really are just a generic description that doesn't refer to any individual experiment. The graph at the left shows the expected outcome if the treatment affects a mechanism that is only involved in the long-term consolidation of the memory. The graph at the right shows the expected outcome if the treatment affects a mechanism that is implicated in early stages of encoding of the memory. Let's think through these scenarios. In the graph at the left, the animal shows intact learning, or a high level of cognitive performance at the test 1 hour after the training and treatment. Basically, the response is equivalent to the response of the control animal. But then the memory is gone by the time of the 24-hour test. So consolidation was disrupted. The graph at the right shows that the learning was impaired at 1 hour. So clearly, there's nothing to consolidate. And the memory is also deficient when tested at 24 hours. In this case, an early learning mechanism was disrupted. So using this kind of approach, we can identify whether our manipulations are affecting those early, perhaps protein synthesis independent stages of the incorporation of the memory, or the later, more protein synthesis dependent stages that affect the consolidation of the memory. And then, with that background, I think we're ready to talk about the role of Krebs. And I'm going to pose a thought question to you. Given that you know about Krebs from back in chapter 5, what do you think would be the effect of a manipulation that blocks Krebs? Would you see the outcome that is depicted in graph number 1 at the left? Or would you get the outcome that is depicted in graph number 2 at the right? And again, somebody's at the back of the class with his hand up saying, oh, pick me. I know the answer. Yeah, right, okay, just kidding. But I do miss talking to the class in person. Far more stimulating than sitting in my study all by myself. And, well, the answer is that blocking Krebs, perhaps with a treatment like actinomycin, the transcriptional inhibitor, would likely not disrupt performance when tested 1 hour after training and treatment, but would be expected to block consolidation expressed in the next 24 hours. The experimental results we might expect would look like the graph on the left. However, there might be other ways in which you could block Krebs that might cause a different set of outcomes. And we're going to see a little bit of that as we explore some experiments in which Krebs was disrupted with transgenic manipulations. But those are coming up in a little bit. First, let's talk a little bit more about the basics of Krebs to add to the information that I already gave you in chapter 5. Let's start by quickly reviewing Krebs, or again, cyclic AMP response element binding protein. It's a transcription factor that binds to DNA sequences called cyclic AMP response elements, or CRE, and thereby increases or decreases the transcription and thus the expression of certain genes. And those genes include CFOS, CJUN, BDNF, tyrosine hydroxylase, the rate-limiting protein, and many neuropeptides like somatostatin and kephalin and corticotropin-releasing hormone, and so on. Krebs is actually closely related in structure and function to CREM, which is cyclic AMP response element modulator, and ATF1, or activating transcription factor proteins. And of course, Krebs is expressed in many animals, if not all animals that I can think of, including everything from invertebrates and insects to humans. Now, we've already seen the kind of sequence of events that activate Krebs. And some of those sequences, including both synapse to nucleus and soma to nucleus models, are illustrated near the bottom of this slide. A signal arrives at a receptor on the cell surface, which leads to the production of a second messenger such as cyclic AMP or calcium, which in turn activates protein kinase. This protein kinase might translocate to the nucleus, or there may be a cascade of these kinase actions eventually translocating to the nucleus, where a kinase will phosphorylate serine 133 on the Krebs protein. The activated Krebs protein then actually dimerizes two Krebs coming together, both of which are phosphorylated at serine 133, and this Krebs dimer binds in the major groove of the CRE region of the DNA. And at this point, it recruits a transcriptional assembly, which we'll see on the next slide. Now, overall, the activation of Krebs and other transcription factors is responsible for constitutive gene expression. That is, maintaining the supply of messenger RNA and protein products that are responsible for ongoing housekeeping and maintenance of metabolic activities of the cell. This actually even includes mRNA and protein synthesis that are implicated in the early stages of plasticity after stimulation in neurons. And of course, activation of Krebs and other transcription factors is responsible for the cascades of genomic signaling that we see when cellular function is undergoing the later stages of plasticity, as we saw in late LTP. The large diagram at the left of this slide really just reinforces the idea that Krebs is a site of convergence of multiple signaling pathways in neurons, all of which succeed in phosphorylating serine 133. Then inside the nucleus, you can see that phosphorylated and dimerized Krebs binds to the CRE sequence of the DNA and assembles actually a transcriptional activating complex. And that complex includes CBP, or Krebs binding protein, which actually co-activates the Krebs, leading to additional binding of CREM and ATF1. The assembly of this transcriptional complex at the CRE leads to activation of additional downstream genes known as CEBPs and IEGs. CEBPs are CCAAT enhancer binding proteins, and IEGs are immediate early genes. These genes encode nuclear proteins that then bind to additional response elements and turn on or turn off expression of additional downstream or late response genes. This is the cascade of activity that is initiated by all of these biosynthetic pathways, ultimately interacting with Krebs to phosphorylate that serine 133. Stop and think about this for a minute. Every time you engage your brain and you process stimuli that you might incorporate into long-term memory, you are activating these pathways. Just the fact that you're thinking about things is activating these pathways to ultimately produce changes in the gene expression for a whole cascade of signaling mechanisms to ultimately modify the structures and functions of spines in your neurons. Now, the CCAAT enhancer binding proteins, or CEBPs, are actually a family of transcription factors that are composed of 6 members: CEBP alpha through CEBP zeta. They promote the expression of certain genes through